having a rectangular cross section, and second beam is I section. So these two types of beams, design procedure of these two types of beams you are going to study. Okay. So design of prestressed beams. So in this we will study two types of designs. First is rectangular beams and I sections. So these two we are going to learn over here in this unit. Okay. So I will tell you the steps. You note down the steps now for designing of rectangular beams, and after we will take the numerical on that. So here steps for designing steps for designing rectangular prestressed concrete beam. Rectangular prestressed concrete beams. So now step 1. You note down these points. These are very important things. Okay. First step is calculate live load moment. Calculate live load moment. We called it as ML. Okay. Then step 2, determine the section modulus. Determine the section modulus. Section modulus is Z. So Z is equal to, how do we calculate Z? You know that M is equal to F into Z. Okay, this is the formula. From where you have got that formula, that is M by I is equal to F upon Y. Okay, so from this relation we got the formula M is equal to F into Z. So now Z is equal to what? Then it will be M into F. The only thing here is you are going to take the live load moment M, and F is the safe stress in concrete. So I am giving here the notation FC, safe stress in concrete. Okay. So now step 3. Step number 3. Choose the convenient depth. Choose the convenient depth depth about 120 of span. And step 4. Calculate width. Calculate width, that is B. Notation is B. From relation Z is equal to BD square by 6. Okay. Once you got the depth from step number 3, okay, when you calculate the depth, then after that calculate the width by using the relation of section modulus. Next is the step 5. Find the prestressing force. Find the prestressing force. This is denoted by letter P. How do we find out the prestressing force? So P is equal to, the formula is average stress in concrete, average stress in concrete multiplied by area of cross section. Okay. So therefore, this P can be calculated as average stress in concrete. So what is the average stress? Just a moment. So now we are at the step number 5. Here we are finding out the prestressing force. It can be calculated as the average stress in the concrete. So average safe stress in concrete. So stress in concrete, the notation we are using is FC. FC is the stress in concrete and FS is the stress in steel. Okay. So now average stress in concrete into area of cross section. So average stress in concrete can be calculated as FC by 2, because you consider the at the start the stress is 0 and right now the stress is FC. So the average is 0 plus FC divided by 2. So it is FC by 2 multiplied by area as it is multiplied by A. Okay. So now this is the finding out the prestressing force, step number 5. After this, your step number 6, and it is calculate calculate area of steel. Calculate area of steel. So how do we calculate the area of steel? So it can be calculated as, you know that again, we know the prestressing force. So force is equal to what? Stress into area. Okay, now we want area. So area is equal to what? It is force divided by stress. So here I will write AS or AST. AST means area of steel. Okay, it is equal to prestressing force, prestressing force divided by stress in steel. Okay, so say stress in steel. So normally this safe stress is of 60% of ultimate stress in steel. Okay. So now suppose in the steel, now suppose 1500 Newton per mm square is the stress in the steel. Then we will take 60% of that. That will be the safe stress in steel. So it can be written as P divided by Fs. So after this, after the calculation of area, our regular steps are there. We will assume suitable bar diameter, and then we will calculate the number of bars, and then number of cables. Okay, so I will write that also here. Assume suitable bar diameter, comma, calculate number of bars and cables. or we can call it as ys. Okay. So now that we will see while solving the problem. Then step number 7. Step number 7 is calculate dead load of beam and dead load moment. Okay. And finally, step number 8, determine eccentricity E. So E is equal to, the formula is 2 into dead load moment 2 md plus ml divided by 2. E is the stressing force divided by 2. Okay. So these are the steps which we are going to use by designing the rectangular stressed concrete beam. So we will see the steps one by one. First, from the given numerical, we will calculate the live load moment. After the calculation of live load moment, we will calculate the value of Z, that is section modulus. So you know this relation F into Z is equal to M. So if we reshuffle that formula, we will get the value of Z. After that, choose the convenient depth above 120 of span. Okay, so convenient depth we will choose. Calculate width B from the relation BD square by 6. Now here you will get the depth of the beam. Okay, after the calculation of depth, you can calculate the width by this relation. Now after that, find the stressing force P. It can be calculated as average stress in concrete into area of cross section. So it is Fc by 2 into A. So why it is Fc by 2? Because it is average stress. Stress is considered from 0 to Fc. Whatever may be the value of Fc. Generally for concrete, this safe stress is 14 Newton per mm square, 1/4 for concrete. And for steel, the stress is 1500, 1200 to 1500 Newton per mm square. Okay. Now calculate the area of steel. After that, step number 6. So this is the formula. Again, area is equal to load upon stress. That formula we have written over here. Step number 7. Calculate dead load of the beam and dead load moment. Step number 8. Determine eccentricity E. So the formula is given. How to determine the eccentricity. Okay. Now using these 8 steps, we are going to design the beam. Okay. So now take down these points, write down. These are the most important points, steps. Now we will take the numerical based on these so that you will understand better. And always see that when we calculate this live load movement, generally we consider the UDL acting along the beam. We don't consider normally the point load. Okay, if the point load is acting, then we convert that point load into the UDL while designing this prestressed concrete beams. It is as per IS 1343. IS code is there separate for prestressing 1343. In that, these details are given. So take the problem. Write down a prestressed concrete beam of uniform rectangular cross section rectangular cross section and and the span of beam is 15 meter and the span of beam is 15 meter. Suppose the total distributed load of 272 kilonewton excluding excluding the weight of the beam. Determine determine the suitable dimensions determine the suitable dimensions in the beam it should not be in the beam, it should be of the beam and calculate area of tendon. Full stop. The permissible stresses are, are 14 Newton per mm square for concrete and 1050 Newton per mm square for steel. So this is the given problem. We will read it once again. A prestressed concrete beam of uniform rectangular cross section and the span of beam is 15 meters. Span is given to you. Supports a distributed load of 272 kN. Now here the distributed load they said to us. But while giving the load they have given in kilonewton 272 kilonewton. So you know the point load, you know the span. So you can convert this point load into the distributed load. Okay. Excluding the weight of the beam. So this load does not includes the weight of the beam, that you need to calculate separately. Determine the suitable dimensions of the beam, calculate the area of tendons. The permissible stresses are, so FC, value of FC is given. Permissible stresses in concrete 14 and FS is 1050, in steel 1050. this much of given data is there with us. Okay, so now we will solve this. First of all, what is given? L is equal to 15 meter. Span is given to us. Then FC, stress in concrete, 14 Newton per mm square. Allowable stress Fs, 1050 Newton per mm square. UDL, uniformly distributed load, is equal to, so point load is 272 kilonewton. Okay, divided by our span is 15, it is in meter, so you will get the total value in kilonewton per meter. It is 18.13 kilonewton per meter. Okay, this is the UDL. So now step number 1, what the first step says, see here, calculate the live load moment. So now imposed load is given to you, that is this UDL. So now the step number 1, we will calculate the live load moment. So I will write here moment due to live load ml. So ml is equal to, it is WL square divided by 8. So W is 18.13 into 15 square divided by 8. So solve it now and let me know the answer. (509.90 kilonewton meter). This is the moment due to live load. And what is our step number 2? Find the section modulus. Okay. So section modulus. Z is equal to, what is the formula for section modulus? Is ml divided by x. So it is 509.90 into 10 raised to 6. So Newton mm divided by x is 14. It is in Newton per mm square. 36.42 into 10 raised to 6. Okay. So 36.42 into 10 raised to 6 mm cube. This is the value of section modulus Z. Then what is our step number 3? Calculate the depth of the beam. Okay. Calculate the depth of the beam. So what is the depth now? Depth of beam D is equal to, how much it is? 1/20th of span. So D is equal to 1/20 into span is 15 into 10 raised to 3. So we will get the depth in mm. आन्सर सांगा लवकर. 750. So we got the depth as 750 mm. So these are our three steps. This is your step number 1, this is your step number 2, this is your step number 3. Now what is our fourth step? If we go back and we look to the fourth step, after this depth calculation, our next step is calculate the width from the relation z is equal to bd square by 6. So now we will calculate the width. So calculate the width now. Width b, okay. So width b of the beam. So now z is equal to bd square by 6. So we know the value of z. It is 36.42 into 10 raised to 6, which is equal to b as it is into d. So what is the depth now? So here we will take, suppose now this depth, whatever we have calculated over here, this is 750 mm is the depth. Okay. So this is, we have taken this as a overall depth of the beam. So now here small d is there. So we require effective depth. So we will assume that effective cover is 50 mm. So it will be 700 square. And here you can say, assuming effective cover is 50 mm. Okay. We assume this. So now therefore, what is the value of B? Calculate the value of B now. What is the value? So 445. 445.95. So we will take 445.95 mm. So we round up this value to 450 mm. So this is the value of B. Now what are our section dimensions? So the beam of cross section, how much? Its width is 450 mm by 750 mm. So these are the dimensions of our beam. Okay. So now we will think about the steel. Once we got the dimension, now we will think about the steel, providing the steel. So here, next step is prestressing force. Prestressing force. Prestressing force P is equal to, it is Fc by 2 into area. So P is equal to this 14 by 2 into 450 into 700. Oh, sorry. Okay, is it right? now after the calculation of this prestressing force, so this is the value of prestressing force. Calculate the area of steel AS. Area of steel AS. So this is how much? Step number 3. Now this is your step number 4. This is your step number 5. And this is your step number 6. Area of steel AS. So area of steel AS or AST you can say. AST is equal to, it is 2360 into 10 raised to 3 divided by Fs. So first of all I will write the formula so that it will be easier for you. So the formula is, it is prestressing force P divided by stress in steel. So which is equal to prestressing force is 2360 into 10 raised to 3 divided by, this is 1050. Therefore area of steel AST is equal to 0.61. Okay. So this is the area of steel which we got. Okay. So I assume that, so AST is equal to 2247 point, how much it is, 61 or something. So assume how many? Assume 10 mm bar diameter. Assume 10 mm bar diameter. Now calculate the number of bars. So number of bars or number of tendons. Number of bars how much? It is 2247.61 divided by pi by 4 into 10 square. Assume 10 mm bar diameter. So let me know the answer. How many bars are required? 28.64. Okay. 28.64. 28.64. So we will round up this bar to 30 numbers. Okay. 30 bars of 10 mm diameter are required. So then number of cables. Number of cable. Okay. So in a single cable we are going to provide the 10 bars. Okay. In a single cable, in one cable we are going to provide the 10 bars. So for 30 bars how many cables are required? 3 cables are required. The number of cables are equal to, here 30 divided by 10. Okay. So how much? 3 numbers. So we are going to provide the 3 cables. Okay. समजते का? नंबर ऑफ बार्स पर्यंत तुम्ही कॅल्क्युलेशन आधी सारखंच केलेलं आहे. देयर इज नो चेंज. बट आफ्टर द कॅल्क्युलेशन ऑफ नंबर ऑफ बार्स वी आर गोइंग टू कॅल्क्युलेट द नंबर ऑफ केबल्स. आपण काय कॅल्क्युलेट करतोय? नंबर ऑफ केबल्स. एका केबल मध्ये किती बार आहेत? 10 बार आहेत. ओके. यू कॅन टेक 8 to 12. You can take 8 number of bars in one cable, or 10 number of bars, or 12 number of bars. Okay. So here we have taken 10 number of bars. So for 30 bars, how many cables are required? 3 cables are required. Okay. So finally we can write over here, provide how many bars? Provide 30 bars of 10 diameter, or 3 cables, each of each consists of 10 bars. Okay, so I will write here, provide 3 cables, each consists of 10 bars of 10 diameter. Okay, of 10 diameter. So this is your reinforcement. So if I show you in the diagram what is this exactly, then suppose now this is your beam and this is the neutral axis. So below the neutral axis steel is provided normally. So here there is one cable, second cable and third cable, and this each cable is consist of how many bars? 10 bars. So total number of cables are 3. 10 bars in each cable, so total bars are 30 bars. This is the width, which is 450 and overall depth it is 750. Okay, so here you can see these are the 3 cables. So in this way, in this cable the bars will be there. Okay, so in this cable now the bars will be placed like this. Whatever I have shown over here, these are the bars. In the cable the bars are placed like this. Okay, so in this way it is provided. So now the next step is step number 7, movement due to dead load. Moment due to dead load. So first calculate dead load. Dead load is nothing but self weight of the beam. So how do we calculate the self weight? Take the cross sectional dimensions. It is 0.45 into 0.75. It is per meter length. Okay. So it is per meter length. What is the answer? 8.44 kilonewton per meter. Okay. Now calculate the dead load moment. MD is equal to, it is W L square by 8, which is equal to 8.44 into 15 square divided by 8. It is 237.5 30. Okay. 237.30 kilonewton meter. So this is the dead load moment. Now after that, last step, eccentricity calculation. So eccentricity E. So E is equal to 2 md plus ml divided by 2p, which is equal to 2 into dead load moment md is 237.30, okay, plus ml. What was our live load moment? What was the value of that? What was the value of live load moment? 509. Okay. So 509.90 and divided by 2 into prestressing force we are going to consider over here. So what was the value of prestressing force? It is 2360. Now after solving this you will get the value of eccentricity E. Let me know the value. 0.208 meter. So it is 0.208 meter. So it will be 208 mm. This is the eccentricity. 208 mm. Okay. So this is the last step. This is how we are going to design the prestressed rectangular sections. So now right from step number 1, I will give you 2 minutes. See all the steps, and if you are having any doubt, any difficulty in any of the steps, then ask me the question in chat. So now I will give you 2 minutes. See all the steps right from step number 1 to the last step. This is the design procedure as per IS 1343. This is the IS code for prestressed concrete. So now the next thing is design of I section. Design of I section beam. Okay. So this is design procedure as per IS 1343. Write down, take these points. The following points may be noted in the of I section stressed concrete beam. Full stop. The Indian Standard Code of Practice has made following recommendations. Following recommendations. Okay. So the recommendations are, here step number 1, safe stresses. So these are the safe stresses which are in concrete, that is the safe compressive stress in concrete, then uh, safe maximum compressive stress at service stage, and then permissible tensile stress. These are the three types of stresses which are induced in the concrete. Okay. So first, when we talk about the safe stresses are there in concrete as well as they are there in the steel. So first we will consider concrete. First, at transfer, so at the transfer of prestress, at transfer, the compressive stress is Fr, maximum safe compressive stress is Fr, it is 0.5 FCK. This is 0.5 FCK. Second, at service, at service, it is 0.4 FCK. At service, it is 0.4 FCK. Okay. Then next is the permissible tensile stress. This is equal to, the notation for this is Ft, 0.129 under root FCK. So these are the stresses in concrete at transfer, at service, and allowable tensile stress. Okay. Similarly, in steel, so the safe stress in steel is 60% of uh, 60% of ultimate stress and should not exceed 80% of ultimate stress. Okay. So the safe stress in steel is 60% of ultimate stress, and it should not be exceed 80% of ultimate stress. That is the safe stress in steel. Generally, it can be taken as in the range of 60 to 80%. That is the meaning. The ultimate stress the ultimate stress may be taken as 1500 Newton per mm square. So safe stress is 1500 into 60%. That will be your safe stress. Okay. Here the loss of prestress loss of prestress may be taken from 15% to 20%. Okay. So loss of prestress. So at transfer, whatever may be the prestress, so at service the same prestress will not be there. The losses will occur, and those are in between 15 to 20%. Okay. So, step number one. Then for steel, for concrete, I can say that this is your step one. We will say this is your step two for steel, and now step three. What is the step three? Find the live load and moment due to live load. Find the bending moment ml due to live load. This is your step number three. Step number four. Calculate dead load moment MD, which can be taken as 20% of live load moment. Okay. So now step number five. Calculate total bending moment calculate the total bending moment. This is called as MT, which is equal to md plus ml. This is your step number 5. After that, step number 6. The the overall depth of B is D is equal to K into under root MT, okay, where where D is equal to overall depth, K is the coefficient, K is the coefficient between 30 to 45, and generally this value is taken as generally K's value is taken as 35, and MT is nothing but it is total bending moment. Okay, so this is your step number 6. Now next is the step number 7. Approximate final prestressing force. Approximate final prestressing force. It can be calculated as P is equal to P is equal to total bending moment divided by 0.65 d. 0.65 d. Here d is not small d, capital D, which is equal to mt divided by 0.65 d. This is your step number 7, calculation of stressing force. Then step number 8. In the step number 8, calculate the area of concrete required. Calculate area of concrete required. So area of concrete here you can say AC, area of concrete required. This is the area of concrete required, which is equal to P divided by 0.5 FC. So the same formula is there. FC by 2 into A आपण बघितला होता ना formula. Last time we have seen this formula. P is equal to what? in the rectangular section. It is fc by 2 into a. Now we want it for a. We want it for a. So it will be 2p divided by fc is equal to a. So 2 खाली जर पाठवायचं असलं तर काय होणार आहे 1/2 बरोबर ना 1/2 होणार आहे हे जर 2 खाली आलं तर so now if I divide by 2 at numerator and divide by 2 at denominator, then it will be 1/2. So it is p divided by 1/2 fc is equal to a. This will be the formula. That is the same formula which is written over here. Okay. So now step number 9. The thickness of flange. Remember, this is I section. The thickness of flange and width may be chosen from 120 mm to 150 mm. Okay, full stop. So from geometry of I section, we can find out the width of flange. Right now you write down the steps. By solving the problem you will understand it thoroughly. Then step 10. Area of tendon. Area of steel oblique tendon. So AST is equal to this force divided by safe stress in steel. Okay. Then step number 11. Corresponding to the finally adopted dimension, finally adopted dimension of the beam section can be checked for safety for each of the following cases. What are the cases? A. Beam is subjected to beam is subjected to initial distressing force and dead load. This is for checking of the beam. Second, beam subjected to the final prestressing force due to dead load and live load. So these are the steps while designing the I section. Okay. So I will give you 1 minute. Please read all the steps right from the start to step number 11 so that we will take one numerical on this. Design the prestressed concrete I section. Design the prestressed concrete I section for following requirements. First, span is equal to 15 meters. Second, superimposed load. Superimposed load means it is live load. It is 35 kilonewton per meter. Then third, cube strength of concrete. Cube strength of concrete after 28 days is equal to, means what? This is FCK, 35 Newton per mm square. Fourth, safe stress in concrete at prestress transfer at transfer of prestress Fr is equal to 0.5 FCK. And fifth, safe stress in concrete that is Fc is equal to 0.4 FCK. Total loss of prestress total loss of prestress is equal to 20%. Allowable tension stress allowable tension stress or tensile stress in concrete is equal to, this is Ft, the notation for this is Ft, which is equal to 0.129 FCK. Okay, still the problem is going on. This is the given data. We have not started the solution. So these points are given 7, then 8. Ultimate stress in steel. This is given as 1500 Newton per mm square. Ninth, safe stress in steel is equal to 60% of ultimate stress. Okay. So this much is the given data. Now we need to design the I section. So to design the prestressed concrete I section for the following requirements: span is given, live load given, FCK value is given, safe stress in concrete at transfer, it is 0.5 FCK, safe stress in concrete 0.4 FCK, total loss of prestress 20%, total allowable tensile stress in concrete 0.129. Okay, under root FCK 0.129 under root FCK. Next is the ultimate stress in steel 1500 and safe stress in steel 60% of this 1500. So this is the given data. Now we will solve the problem. Step number 1, calculate all the stresses first in steel and concrete. Okay. So compressive stresses, stress in concrete at transfer at transfer, that is FR, which is equal to 0.5 FCK, which is equal to 0.5 into FCK is 35. So this value is 17.5 Newton per mm square. Okay. Then stress in concrete at service at service, which is equal to 0.4 FCK, which is equal to 0.4 into 35. How much it is? 0.4 into 35, 14 Newton per mm square. Next, allowable tensile stress in concrete or maximum tensile stress in concrete Ft is equal to 0.129 under root fck, which is equal to 0.129 under root 35. Therefore, Ft is equal to, what is the value? So it is 0.76 Newton per mm. This is the tensile stress. So these are the stresses in concrete at transfer, at service, and allowable tensile stress or maximum tensile stress. Okay. So हे काय ट्रान्सफर म्हणजे at the time of transfer of prestress, what is the stress in concrete? It is 0.5 fck. ज्या वेळेला prestress देत आहोत त्यावेळेला. At service means what? After providing the prestress, everything is done, and that member is now giving the service, or that member is applied in some bridges or anywhere. Then at that time, in its service period, okay, its stress is 0.4 fck, which is 14. So both these are the compressive stresses at transfer and at service. And the maximum tensile stress in concrete is 0.76. Remember that all these three stresses are related to concrete only. One is at transfer, second is at service, and third is allowable tensile stress. Now next, we will see about the steel. So safe stress in steel, safe stress in steel is equal to 60%. So 0.6 into what? Ultimate stress 1500. So what is the 60% of that? 1590 na? So 900. Is it correct? 900 Newton per mm square. Okay, now the next step, moment due to live load. Moment due to live load, that is ml is equal to wl square by 8, which is equal to load, how much it is given? Superimposed load is 35 into span given, it is 15 meter, wl square divided by 8. So now wl square by 8, what is the answer? Calculate it. What is the answer now? So the answer is 984.37. Okay, 984.37 kilonewton meter. This is the moment due to live load. Then approximate moment due to dead load. Calculate the approximate. सोडायचं आहे का मग बीच्या ना पण ठीक आहे. Okay, so there is one announcement from for you. We will stop our lecture right now here, and there is a link which is sent on your group. You have to join that session immediately, and after joining the session, take the screenshot and send it to your class coordinator.